Hi. In the last video, we spent some time getting the Control ROM Control Breadboard actually working. At least I think it's working. It's mostly working. There are some issues that I do need to take a look at. For example, the most significant bit remained on after cycling through all the different addresses. I want to look at that and determine what's going on with that. I know I'm only pulling it from the counter, not from the multiplexer, so that's likely contributing into that. There's a number of bodge, if you will, wires that are on that breadboard that I need to clean up. These were the result of my debugging. I want to re-add the control signal LED and get those wired up. Those are going to be instrumental in continuing to debug. And then I want to add the instruction register input wires into the muxes. Now, I'm hoping that won't take too long and it'll leave us plenty of time to create the schematic for the Control ROM module and build at least one of those. Let's get right into that.
Hi, I'm Adam. I'm still building a 16-bit computer from scratch. I'm no expert here. I make lots of mistakes. So many mistakes I've actually had to reboot my computer build. I hope you will find my journey interesting, and I hope you will join me as I learn along the way. Okay, the first order of business is to research that LED right there. If I hit reset and let it count through, that LED stays on. So what I want to do is I want to take a look at all of the counter outputs. I recall that I hooked this up directly to the counter. And they are all going to be high. Now the behavior here is going to be based on the way these counter ICs work. And it's important to understand that once it's getting ready to carry over, that signal that is normally high comes low prior to the rising edge of the clock so that everything increments at the same time. And so it's the falling edge of that carry out, which is then turning around and resetting the set reset latch for copying, which takes the entire circuit out of copying mode. Now, is this a problem? I don't know. And I won't know until I actually get an EEPROM and SRAM hooked up to this and actually go through the cycle, get myself a testing bus put in place where I can actually query the contents of the SRAM and make sure that last byte is actually being copied. I probably could go back to the emulator and create a purpose-built test file and use that in order to determine if things are copying. If that last byte was 0, it's entirely possible that it was not copied properly. But I did also fill it with FF and check it with that, and I think it actually worked, or at least I recall that it actually worked. So maybe I'm good, and I just need to get this settled. Well, enough yapping. Let me get these bodges cleaned up. I need to get this signal actually wired up here to the multiplexers and make sure that that's being handled properly, which means I need to actually pull that signal over as well back to here. So I will get that done, and then we'll talk about getting the instruction register inputs pulled from here over onto the multiplexers as well. Okay, the first thing I want to do is try to clean up some of these bodges. Okay, let's give that a shot. On reset, yeah, it's counting and then it now goes to 0. Yep, I'm liking that. That's good. So I just need to now replace this wire completely. All right, now let's deal with the instruction register inputs. I'm going to start with bits C, D, E, and F. F is unused. Bits 8, 9, A, and B. Bits 4, 5, 6, and 7. Bits 0, 1, 2, and 3. Okay, so the challenge now is that each of these signals needs to be brought either high or low, because while I did extend them out here, they are still floating. So I'm going to tie them in an alternating pattern, high and low, just to make it easy to identify that it's actually got the right pattern. Now, therefore, once I run this and perform my reset, I have an alternating set of bits here that I can use to confirm that I've actually got the wiring correct. Okay, what's next? Okay, the next thing on the list is going to be to refit these control LEDs to make debugging just a little bit easier. They're already wired up coming from the line driver, but I don't have any inputs, so I need to start pulling those. And I'll use temporary hookup wires to get through that. Pin 2 here is going to come from bits counter output A. That'll be this pin here, which I can pick up down here and bring it to there. And then finally, we've got the copy clock. Now the copy clock is available on and 3 pin 3. And that's going to be here, but this should have something connected to it already, I would think. What did I do? What did I do? What has copy clock as an input? That should be the shifter. So up here, what is that hooked up to? That's an inverter. That's the raw clock. And the further on up, that's the D-type latch. That should be the raw clock. So I messed this up big time. Let's see what I have to do to fix that. Okay, let's power this on and make sure that still works. Yeah, something broke. All this troubleshooting, and it turns out the inverter wiggled its way out of the breadboard. Nice. Well, how did I manage to get that wiggled out? That IC was loose. It wasn't seated properly. All right, I'm going to take a few minutes here and I'm going to extend wires to take care of all of these signals. And then after that, I've got some changes I need to make to the schematic. These are just LEDs, the blue ones for the control signals. They don't really bring much value, I don't think. I think the clock speed is high enough that I can't actually discern anything from them. I may end up retiring those. Okay, so for debugging purposes, I made one change on the breadboard that is not reflected in the schematic and is not reflected in the emulator. I don't want to catch those up to keep them congruent. So let me make those changes now. This is incorrect. Okay, and as I was going through the code, I did actually find an error related to the multiplexers on the emulator. It was taking a 16th bit from the instruction bus off the instruction register, which was incorrect. So I corrected that while I was at it. Perfect. Okay, the next thing for today is going to be to work on the schematic for the Control ROM module. Now, this is one of the actual modules themselves that have the EEPROM, the SRAM, the shifter, and latch associated with it so that I can turn around and get data off the EEPROM into the SRAM and then do a lookup on that and latch that for a clock cycle. Like I did before, I'm going to use the code as the basis for this, and I'm going to lay all of this out and make all of the appropriate connections. I've already gone through and checked all the symbols to make sure that all of my components are represented and they're there, so that's a good thing. So with that, let me get right into one of these smaller EEPROM modules. Placing components. LED driver. Control signals. Address pin inputs and signal outputs. EEPROM. Internal control signal bus. SRAM. Shift register. Control signal cleanup and latch register. Latch. Power, ground, and cleanup. And finally, we get to the point where it's time for the electrical rules check. Okay, so I did something wrong with that. Okay, not exactly sure what to do with that. So there's some new functionality in the version of KiCad I'm using, which requires special naming conventions for members of a bus, which this is the first time I'm using in a schematic in this project. So a little bit of cleanup, and I have a clean ERC check now. Nice. Okay, here's the breadboard for the Control ROM circuit. Here's the ROM over here. There's the SRAM. That's the shifter. That is the line driver that will then be used to control what goes from the shift out onto this bus over here. This bus being a latch, and then from the output of the latch to a line driver to drive the LEDs. Now, this is an LS line driver. This is an HCT line driver. I'm using the LS line driver because I'm only driving LEDs here and I don't have enough HCT and dip to do everything that I want to do. So I'm going to hang on to these and treat them a little bit as a constrained resource and use the LSs where I can. Driving LEDs is certainly a valid use for those. And the HCT logic can drive the LS logic without any issues. All right, so behind that, I now have an output of all the different hookups that I need to do. This is not nearly as in depth as the Control ROM control circuit, but it's still very dense. I still have a lot of things I need to fit in here, including my address input, my control pin input, and my signal output. The signal output will come out directly off the latch here. So again, very densely populated board. I'm going to start over here on the farthest and work my way back this way. There are a couple of signals over here that I'm going to need to drag all the way over to this side. And I think I'm going to try to use this channel down here in order to snake two of the signals across. Long story short here, I'm going to get going on this, just similar to what I did with the Control ROM Control, and start getting the shorter things wired up, and then I'll deal with the longer things as I get to them. So I'm going to start over here and work my way to the right. Okay, I said I was going to start with shorter ones and leave the longer ones for the end, but in reality, this is probably one of the hardest signals to route, so better to get it taken care of sooner than later. That way, it's just simply done. Next up is the shift register. Line driver. SRAM control signals. Switching gears, LED signals. LED line driver. The bus between the line driver, static RAM, and latch, plus the latch output enable. Tying the unused inputs to ground and VCC. Address lines 14, 13, and 12. Bits 11, 10, 9, and 8. Address lines 7, 6, 5, and 4. Address lines 3, 2, 1, and 0. Okay, that should complete the wire up for this EEPROM module. Okay, well, I think the next order of business is to take this EEPROM module and connect it up to this Control ROM Control Module. And I think I want to do it this way up here, because my address lines that are going to feed into here are these brown signals here. So I should be able to jump them together in something like this. It's a little tight, but I think that'll work. All right, that's the easy connection. Next thing is getting all of these control lines up here connected. And they're going to come from multiple different spots down here up to this signal. And I don't have those memorized, and I don't yet have them pulled up here because of the reset button there. All right, so to do that, I'm going to need some pictures of where everything is, and I'm going to have to set these up. So I'll stick some pictures. I'll tell you what, I'll slide this over here. I'll stick the pictures up in the corner up here, and I'll pull them up for myself, and let's just see where we end up with this. Now, theoretically, this gives me everything that I need in order to at least run this through its paces and give it at least a preliminary test. Okay, I've got my clock module hooked up here because there's a latch over here that requires a latch signal, which would normally come from here. So I'm planning on using my little rocker here to do that. What do I really expect to happen when I hit the power button? Well, honestly, not very much. I do actually have to hit the reset to get this lower circuit to run through its paces, but I'm not expecting to see any output up here. It's not wired that way because it's only the output of the latch that drives that. Now, if I happen to be fast enough to hit this while it is copying, I may actually be able to catch a value here, but we'll see how that goes. And I'm pulling 216 milliamps. Okay, let's turn that up as fast as it can go and hit the reset button and see what happens here. Absolutely nothing up here. But is that a problem? I'm not feeling anything hot. It's more than likely this value has zeros here. So I believe it's 1, which is of course buried under all of this. I believe it's the value or address 1 or 2 that has something in it for this EEPROM. So let me program this to be 2 and see if I can't get at least something out. I'm hooked up to the wrong spot here. Ultimately, these need to come down here, so I need to make some more ribbon cables. Let me see if I can steal something. Okay, I did find a couple of cables that should work here. This should be long enough. All right, let's power that on and see how that goes. And yes, I am pushing out address 2, but I'm still not getting anything here. Yes, the 2-bit is high. The address lines that I tested are all low. So I'm wondering if I'm not moving too fast for either the SRAM or the EEPROM. Okay, it's been a couple of days. Let's get methodical here with this. So the way this works is that the shift register shifts out and sends commands to the EEPROM. So I want to make sure that the command associated with getting data off of this is being shifted in properly. So I will reset, and that would be up here on that pin. So I'm expecting to see some high values just like that being shifted in. And that reset. So the next one is going to be the output. Now I'm expecting another 16 bits of zeros. This is high impedance, which may be something to deal with here. And it just went high. That was not 18 clock cycles, I think it was 16 when that started outputting data. And I should see if I keep ticking away here, some high values come across, which I did. Now, I've got to double check the timing of this. Yeah, that came on too soon, which means that my clock cycles here, every one of them is registering. That looks great. Okay. That never came high, or that never came active, I should say. So there's part of the problem right there. So what is going on with that? Yep, never came active. So there's something going on here that's still not getting everything to this. Okay, well, I'm going to save you from a couple of hours of digging and testing and staring at a screen in order to try to figure out exactly what's going on here. Let me show you what I found. I'm going to start by powering on the circuit, and then I'm going to perform a reset. And my logic probe is on the clock input for the EEPROM. And now when I come out of reset, this is the first clock tick. 2, 3, 4, 5, 6, 7, 8, 9, and this is the one that is skipped. So the problem is I'm getting an extra clock tick for the first byte, a 9-bit byte rather than an 8-bit byte. And then if I continue on, there were 8 more clock cycles, and the rest of them work just fine. It's just that first rising edge which is causing me a problem. All right, so why didn't I see this in the emulator? Well, again, it has to do with the linear nature of how the emulator is written and in what sequence each of those connections are made. They are taken one at a time. There's nothing that says go and update all of this all at once. Everything is updated sequentially, and it's a depth first, meaning it will follow that signal all the way to its conclusion, all the way down to the leaf of the tree, before coming back and then executing down the next branch over all the way to the leaf of the tree, and then coming back, and then et cetera, as it goes across. It's going all the way to the leaf and then coming back. And if that same signal is going to the same leaf through different branches, then that's fine, but it gets updated multiple times as a result of that. The big thing here is that it is related to the sequence in which things are wired up as to how that's going to work. All right, a lot of talking, Adam. What's the solution? Well, the problem is that the resetting D-type latch is actually coming out of reset a half of a cycle too soon, causing an extra rising edge on this EEPROM. So this signal here is again the clock, and there's my rising edge as I released the reset or released the clock over here, and that had the same first rising edge as over here. Well, what I need to do is I need to delay this rising edge by half of a clock cycle in order to get that done. Well, if I trace backwards this signal, which is this one here, it comes back to, and I'll use my logic probe as a pointing device, it comes back to the input of this inverter. Well, I'm right at an inverter. Let's take the output of the inverter rather than the input of the inverter and chain that along, and let's reset. So now as I release the clock, I'm no longer getting the rising edge there. And I will reset again, and I will go on to the clock of the D-type latch. I release, that clock signal goes low, which is fine. And when it goes high again, that's now when it's latching the new state. Again, exactly the way I need that to work. So what happens here then? Okay, so here's my release of the clock. That resets my D-type latch. I'm no longer resetting. There's bit 1, bit 2, bit 3, bit 4, bit 5, bit 6, bit 7, and bit 8. And now I don't get a rising edge. So that corrects what I believe to be the fundamental problem, because as you see, I'm now getting values across the LEDs. Now, I originally said that I didn't expect anything to show up there, but because I'm tied to the same clock here for latching the latch as I am over here, which is running this, that's why I'm seeing values here. This I know is working in the circuit, or at least I believe it's working in the circuit. It's certainly a good change here. So I need to go make that change in the schematic, and I'll do that now. Okay, the change here is pretty trivial. I just need to get an inverted copy of this raw copy clock. And then that becomes now the input into the D-type latch. Quick ERC check, no issues. The next thing to look at is the emulator, and I need to make that connection for the input for the clock, pin 3 of that D-type latch, to come from the inverted emulator. And then a quick build, and let's run that through once. Ah, I do have a problem here. I need to see more information now. So my emulator is not congruent, well, may not be congruent with hardware. Okay, I added some code in here just to dump the first 8 bytes of SRAM. I know that the first 3 bytes are in hexadecimal 001313, and so that should give me an indication of exactly what is not aligning here. So let me make this change and run the emulator, and once it's complete, we'll see what shows up. Okay, once again, the expectation is here 001313. I'm getting 00098980. And if you look at those closely, they're off by 1 bit. Okay, so this looks very similar to a situation that I tried to deal with in video 92. I was about 12 minutes into the video when I uncovered the race condition and spent the rest of the video trying to solve that problem. And it looks like I have the same problem again now. And it's entirely possible the root cause of the two are very closely aligned. I'm not certain if the problem itself was this one and I solved it incorrectly, or they're two distinct problems. I'm not going to go back and undo all those changes in order to test this. I have something that is very close to working in real hardware, and while there is a 12.5% penalty for that, I like the way the circuit is shaping up, and I'm not going to make the effort to undo that just to prove that it could work the other way. It all boils down to arguing with success. I just don't feel like it's a good use of my time. Now, I may end up doing that as a separate task. This particular incarnation will continue forward in the build. All right, so what is the problem here? Well, it boils down to how I implemented the EEPROM in software. And I made a mistake here by thinking that while the value should be sampled on the rising edge, in the implementation of the IC, the value should actually be changed on the rising edge, and that's incorrect. I'll throw the read timing diagram up on the screen here. But if you look at it, the transition of any given bit happens slightly after the falling edge of the clock, which is really, I could implement on the falling edge. But the key is that the first bit of the data payload is made available on the falling edge of the last address bit being clocked in, rather than on the rising edge of the next clock cycle. So if I back all of this up by half a clock cycle, all of these signal changes and everything here, that should put the software congruent with the way the hardware is behaving, and certainly in line with how the datasheet indicates that timing should be. Let me make that change. We'll give it a test. Okay, quick change. Let's build this and give it a test together. Perfect.
All right, I'm quite happy with where we've managed to get to in this video. Seeing the hardware and the software work congruent with each other is really actually an amazing accomplishment for me. I am thrilled to see those working together. It gives me confidence going forward that when I order PCBs, that they're going to work exactly the way that I need them to. But there are two things that still need to be done before I can actually start committing this design to PCB. One of which is I need to make sure that the contents of the SRAM exactly match the contents of the EEPROM. To do that, I'm going to employ an Arduino. Once the copy is complete, I should be able to cycle my way through each of those addresses and compare them against what the expected results should be and determine if I've really got a good copy. The second is I need to reintroduce that crystal oscillator. Right now I'm working on an exceptionally slow clock being driven by a 555 timer. If I get that 1.8-ish megahertz crystal oscillator in there, it'll work much faster. Ideally, I'd like to see that 10 megahertz crystal in there. That will be the purpose of the next video, is to do that testing, reintroduce the crystal oscillator, both of them, and perform the appropriate testing on those. We'll look forward to that. We'll see you soon.